When we gaze up at the night sky, we are often filled with a sense of awe and wonder. But have you ever stopped to wonder about the shape of this cosmic expanse we call home? Is it flat like a sheet of paper? Is it curved like a sphere? Or could it be something else entirely? Understanding the shape of the universe is not just about satisfying our curiosity. It's about unraveling the fundamental nature of space and time, about understanding the universe's past and predicting its future. We'll explore the concepts of flat, closed, and open universes, using simple analogies to grasp these complex ideas. We'll journey to the edge of the observable universe and examine the faint afterglow of the Big Bang, known as the cosmic microwave background, to see what clues it holds about the universe's shape. Get ready to expand your cosmic perspective as we embark on this mind-bending adventure to uncover the shape of the universe. Imagine a flat sheet of paper stretching out infinitely in all directions. This is the simplest way to visualize a flat universe. In this scenario, parallel lines remain parallel forever, never intersecting or diverging. The angles of a triangle drawn on this flat cosmic canvas always add up to 180 degrees, just like we learned in geometry class. A flat universe is infinite in extent, meaning it has no boundaries or edges. If you were to travel in a straight line in any direction, you would continue forever without ever reaching a wall or looping back to your starting point. Think of a beam of light traveling through space. In a flat universe, this beam would continue on a perfectly straight path forever. The density of matter and energy in a flat universe is perfectly balanced, preventing gravity from curving space enough to bend the light's trajectory. Now, let's move away from the flat sheet of paper and imagine a balloon. As you inflate the balloon, its surface expands and curves. This is analogous to a closed universe. In this model, space is finite and curved in on itself, like the surface of a sphere. Just like on the surface of a balloon, if you were to travel in a straight line in a closed universe, you wouldn't end up going in a truly straight path. Instead, you would eventually loop back to your starting point, having circumnavigated the entire cosmos. In a closed universe, the angles of a triangle add up to more than 180 degrees. Imagine drawing a triangle on the surface of a globe. The fate of a closed universe is also intriguing. The gravitational pull of all the matter and energy within it would eventually halt the universe's expansion and cause it to contract in a fiery big crunch. Finally, we come to the open universe. Picture a saddle or a Pringles chip. These shapes represent the geometry of an open universe. In this model, space is curved, but instead of curving inward like a sphere, it curves outward, resembling an infinite saddle. In an open universe, parallel lines diverge, and the angles of a triangle add up to less than 180 degrees. This type of geometry can be tricky to visualize, but the key takeaway is that space is negatively curved and infinite in extent. An open universe continues to expand forever. The gravitational pull of matter and energy is not strong enough to halt this expansion, so the universe grows increasingly cold and diffuse over time. But how do we determine which shape our universe actually takes? To answer this, we need to look at the evidence. The shape of the universe isn't just a matter of abstract geometry. It's intimately tied to the universe's density. Imagine a cosmic scale, with the universe's matter and energy on one side, and a critical density value on the other. This critical density represents the tipping point between the three possible shapes. If the universe's density is greater than the critical density, the gravitational pull of matter and energy would be strong enough to eventually halt the universe's expansion and cause it to collapse in on itself. This scenario corresponds to a closed universe. Conversely, if the universe's density is less than the critical density, the gravitational pull wouldn't be strong enough to stop the expansion. The universe would continue to expand forever, albeit at a decreasing rate. This scenario corresponds to an open universe. And what if the universe's density is precisely equal to the critical density? This is where things get interesting. In this perfectly balanced scenario, the universe would continue to expand forever, but at an ever-decreasing rate, asymptotically approaching a standstill but never quite reaching it. While density plays a crucial role in shaping the universe, it's not the only factor at play. The universe's expansion rate also contributes to its geometry. Think of the universe as a dough being kneaded and stretched. The initial density of the dough is essential, but so is the force with which it's stretched. This stretching force, in the context of the universe, is the expansion rate. A rapid expansion rate would counteract the gravitational pull of matter and energy, pushing the universe towards an open saddle-shaped geometry. Conversely, a slower expansion rate would give gravity more time to rein in the expansion, potentially leading to a closed, spherical universe. To probe the universe's shape, we need to look back in time, to the universe's infancy. Fortunately, the universe has provided us with a remarkable relic from its earliest moments: the cosmic microwave background, or CMB. The CMB is a faint afterglow of light and radiation that permeates all of space. It originated approximately 380,000 years after the Big Bang, when the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms. This event allowed photons, or particles of light, to travel freely through space for the first time, creating a faint afterglow that we can still detect today. The CMB is a treasure trove of information about the early universe. Its temperature, which is remarkably uniform across the sky, provides strong evidence for the Big Bang theory. But the CMB also contains subtle temperature fluctuations, tiny variations in temperature from one part of the sky to another. Think of the cosmic microwave background, or CMB, as a vast cosmic tapestry woven with subtle patterns and imperfections. These imperfections, the temperature fluctuations, are not random. They are remnants of tiny density variations in the early universe, which acted as seeds for the formation of galaxies and other large-scale structures we observe today. The size of these temperature fluctuations, as observed in the CMB, depends on the geometry of the universe. In a flat universe, light from the CMB would have traveled in straight lines for billions of years, preserving the size of the fluctuations as they appeared in the early universe. By carefully measuring the size of these temperature fluctuations in the CMB, cosmologists can determine whether the universe's geometry is flat, closed, or open. In 2003, a team of astronomers led by Paolo de Bernardis and Alessandro Melchiorri analyzed data from the BOOMERanG experiment, which was a balloon-borne telescope designed to study the cosmic microwave background, or CMB. Their findings sent ripples through the cosmological community. Melchiorri's team reported that the temperature fluctuations in the CMB appeared slightly smaller than expected in a flat universe. This anomaly, dubbed the Melchiorri Anomaly, hinted at the possibility of a closed universe, where the curvature of space magnified the apparent size of the fluctuations. Some cosmologists argued that the anomaly was a genuine signal from the early universe, evidence for a closed or slightly curved universe. Others remained skeptical, suggesting that the anomaly could be attributed to systematic errors in the data or limitations in the analysis techniques. Despite the intrigue surrounding the Melchiorri anomaly and other potential deviations from flatness, the current consensus among cosmologists is that the universe is indeed flat. This conclusion is based on a wealth of observational evidence from the CMB, as well as other cosmological probes. The prevailing cosmological model, known as the ЛCDM model, incorporates a flat universe as one of its fundamental assumptions. This model, which includes dark energy represented by the cosmological constant lambda and cold dark matter, or CDM, has been remarkably successful in explaining a wide range of cosmological observations. The ЛCDM model's success in explaining these observations has solidified the notion of a flat universe as the leading contender in the cosmic shape race. While the evidence currently points towards a flat universe, the quest to understand the universe's shape is far from over. Cosmologists continue to refine their measurements of the CMB and other cosmological probes, searching for subtle clues that might reveal deviations from flatness. New generations of telescopes and experiments, both on Earth and in space, are being designed with the goal of measuring the CMB and other cosmological parameters with unprecedented precision. These advancements promise to shed new light on the universe's geometry and potentially challenge our current understanding of cosmic evolution. The universe is full of surprises, and the shape of our cosmic home is no exception. The quest to unravel the mysteries of cosmic geometry is a testament to humanity's insatiable curiosity and our relentless pursuit of knowledge about the universe we inhabit. The question of the universe's shape is a profound one, touching upon the very fabric of space and time. While the current evidence strongly suggests a flat universe, the possibility of subtle curvature, or even more exotic geometries, remains an active area of research. As we continue to explore the cosmos, we must remain open to new discoveries and unexpected twists in the cosmic narrative. The universe is a vast and mysterious place, full of wonders yet to be uncovered. The pursuit of knowledge about the universe's shape is not merely an academic exercise. So the next time you gaze up at the night sky, remember that you're looking out at a universe of wonder, a universe that continues to challenge our assumptions and inspire us to explore the unknown.